Welcome to Understanding Parsers and Grammar Composition with Python Lark. I'm Omar Hosni, and in this presentation, we'll demystify parsing concepts that every Python developer should know. Parsing is the process of analyzing a string of text and converting it into a structured representation. Every time Python runs your code, it parses it first. Every time you read a JSON file, a parser converts that text into a dictionary. As developers, we encounter parsing everywhere. Configuration files, query languages, log analysis, data transformation, and domain-specific languages all require parsing. Understanding parsers unlocks the ability to build powerful tools. A parser has three main stages. The lexer, also called the tokenizer, breaks text into tokens. The parser applies grammar rules to organize tokens into a tree, and the result is an abstract syntax tree, or AST, that represents the structure of the input. The lexer reads characters and groups them into tokens. For example, in the expression host equals localhost, the lexer produces three tokens: the name host, the operator equals, and the string localhost. Each token has a type and a value. The grammar is a set of rules that defines the structure of a language. It tells the parser what combinations of tokens are valid. Think of it like the rules of English grammar, but for your custom language. Most grammars use EBNF notation. A rule name followed by a colon defines a pattern. The question mark means optional. The star means 0 or more. The plus means 1 or more. And the pipe symbol means or. These simple building blocks can describe complex languages. An abstract syntax tree, or AST, is a tree representation of your parsed input. Each node represents a grammar rule, and leaves represent tokens. The tree captures the hierarchical structure that was implicit in the flat text. A transformer walks the tree bottom up, converting each node. You define a method for each grammar rule. The transformer calls leaf methods first, then works upward. This is how you convert a parse tree into useful Python objects like dictionaries or custom classes. Visitors and interpreters are alternative tree walking patterns. A visitor traverses the tree for read-only analysis, like type checking. An interpreter walks top-down with explicit control over which children to visit, perfect for executing code or rendering output. Grammar composition lets you build complex parsers from smaller, reusable grammars. Each subgrammar handles one format or concern. A master grammar imports them with namespace prefixes to prevent naming collisions. This is modular design applied to parsing. The indenter is a special post-lexer that handles whitespace significant languages like Python. It monitors indentation levels and injects special indent and dedent tokens. This transforms flat text with whitespace into structured blocks that the parser can understand. Lark is a modern parsing library for Python. It is pure Python with zero dependencies. It supports multiple parser algorithms, including fast LALR and flexible early. It auto-builds parse trees, handles ambiguity, and has a clean Pythonic API. Using Lark is simple. You write a grammar string, create a Lark instance with your chosen parser type, and call parse. The result is a tree object you can print, transform, or inspect. The grammar uses a .lark file format with rules and terminal definitions. Lark's transformer class is where the magic happens. Each method name matches a grammar rule. The vargs decorator with inline equals true unpacks children as method arguments. Return values replace the tree nodes. It is intuitive and Pythonic. Lark has powerful advanced features. Merge transformers combines multiple transformers with namespace prefixes. Save and load caches the parser for fast startup. The override and extend directives let you modify imported grammars. These features enable production-grade parsers. Let us build a real parser. Production systems generate logs in multiple formats. Syslog for system events, JSON for structured application logs, and custom formats with key value pairs. Analyzing logs across these formats requires a unified parser. Our approach uses grammar composition. We will create 3 independent subgrammars, one per format. A master grammar imports all 3, and merge transformers combines their processing logic. Each format team can work independently. The syslog grammar defines the traditional log format. An entry has a timestamp with month, day, and time, followed by hostname, process name, PID in brackets, and a message. Each part is defined as a terminal with a regex pattern. The JSON log grammar parses structured log entries. It defines an entry as curly braces containing comma-separated key value pairs. Values can be strings, numbers, booleans, or null. We import common terminals like escape string from Lark's standard library. The custom log grammar introduces 2 powerful directives. The extend directive adds trace and fatal to the existing log level terminal. This is grammar extension, not replacement. The template rule kv pair defines a reusable key equals value pattern. The master grammar is elegant in its simplicity. It imports the entry rule from each subgrammar using Lark's import syntax. Each import gets an automatic namespace prefix. A log entry is then defined as any one of the 3 formats. Each format gets its own transformer class. The syslog transformer has one method, entry, decorated with vargs inline. It receives the parse tokens as arguments and returns a normalized Python dictionary with format, timestamp, host, process, PID, and message fields. The JSON log transformer handles JSON entries. The pair method extracts key value tuples. Type conversion methods handle strings, numbers, and booleans. The entry method assembles everything into our unified dictionary format with standard fields. The custom log transformer is straightforward. The kv pair method returns key value tuples. The entry method combines the timestamp, log level, and key value pairs into our unified format. Notice how each transformer is completely independent. Here's where composition shines. Merge transformers takes a base transformer and keyword arguments mapping namespace prefixes to format-specific transformers. Lark automatically renames each transformer's methods to match the namespace. The result is a single unified transformer. For production use, Lark can serialize the parser with save and restore it with load. Our compiled parser is just 11 kilobytes. Loading from cache is near instant compared to reparsing the grammar. This is critical for log processing pipelines that start frequently. Let us see log merge in action. We feed it mixed log lines, syslog, JSON, and custom format. The parser automatically detects each format. The merge transformer normalizes everything into unified dictionaries, 7 entries across 3 formats, all processed in a single pass. Let's recap what we've learned. Parsers convert text into structured data using grammars. Lark makes parsing accessible with a clean Python API. Grammar composition enables modular, reusable parser design. Transformers convert parse trees into useful data. And production features like caching make Lark ready for real-world use. Thank you for watching. You can find the Lark library on GitHub at github.com/larkparser/lark. All the code from this presentation is available in the Use Cases directory. Happy parsing!